This is the continuation of logistic regression part 8. Today I will discuss Rsquared. In multiple regression, R-square, I denote it by Rm square. M stands for multiple, represents the proportion of variation in the dependent variable accounted for by the independent variable. It is the ratio of the regression sum of square to the total sum of squares. When the residuals from multiple regression can be assumed to be normally distributed, then R square M equal to L small lp minus small l naught divided by small l naught, where small l naught the log likelihood of the intercept only model. That means this is a log likelihood containing only intercept term, and small lp this is log likelihood of the model that includes the independent variables, that is L beta curl hat. So since small lp varies from small l naught to 0, then R square m varies between 0 to 1. So this is your homework. Check that Rm square varies 0 to 1. If you define Rm square Lp minus small l naught by l naught, then your Rm square varies 0 to 1, assuming that residuals follows normal distribution. Unfortunately, when R square L, that is R square for logistic regression, here capital L stands for logistic regression, is calculated using the formula small lp minus small l naught by small l naught it does not necessarily range between 0 to 1, because the maximum value of small lp is not always 0, as it is in multiple regression model. So, or as you know, for logistic model, the maximum value of small lp is small ls. This is a log likelihood of saturated model So, for logistic model, R square L equal to small lp minus small l naught divided by small l naught minus small ls. This introduction of small ls into the model or this small ls into this formula causes a degree of ambiguity with Rsquare that does not exist with Rm². This ambiguity is due to the fact that the value of small ls depends on the configuration of independent variables. Check that this Lsquare lies between 0 to 1. This is your another homework. Consider a logistic regression problem consisting of binary dependent variable and a pool of 4 independent variable the data for this example are given in the following table. So this is the example where y is a response variable, and here we consider 4 explanatory variables. Now notice that if only x1, x2 are included in the model, the data set may be collapsed because the number of repeats, in case the value of small ls will be less than 0. Check. This is another homework. However, if x3 or x4 are used, then we see that there are no repetition and the value of small ls will be 0. You check it. This is another homework. Hence, denominator of RL square depends on which of the independent variable is used. So, this is the note. The denominator of RL square depends on which of the independent variables is used. This is not the case for Rm square. That means R square for multiple regression. This ambiguity comes into play especially during subset selection. So this is another note. This ambiguity comes into play especially during subset selection. It means that as you enter and remove independent variables, the target value Ls can be changed. Hosmer and Lemeshow in 1989 recommend against the use of RL square as a goodness of fit measure. However, we have included it in our output because it does provide a comparative measure of the proportion of log likelihood that is accounted for by the model. Just remember that an RL square value of 1 indicates that the logistic regression model achieves the same log likelihood as saturated model. However, This does not mean that it feeds the data perfectly. Instead, it means that it feeds the data as well as could be hoped for. Thank you. We will continue logistic regression in our next class. Stay with us. Thank you.